Good morning, students. In the last class, what we have seen is uh, we have seen a single pane window problem, and we have solved it, and we have got the value for Q. We've got the value for Q as 266 watts. The same problem we will take today, and then we will do it for a double pane window. Instead of one pane here, if I have double panes, how my problem will be like? We will try to look at that. Let me take that problem. This is a double pane window problem. Now you can see this problem. Here it is, and let's read it. Yeah, here what you have is you have area of heat transfer. This will be your area is equal to 0.8 into 1.5 meters square. This is heat transfer area perpendicular to the direction of heat transfer. Uh, Along with that, you have a double pane window. The double pane window will have two glass planes here. Okay, this is glass plane 1, and the glass plane 2 will be something like this. Okay, there are two glass planes here, and these two glass planes are entrapping air in it. You can see these are 4 mm thick. These are 4 mm thick. 4 mm thick. Then this is a glass having K is equal to 0.026 watt per meter Kelvin. And then you have H1 and H2. The H1 value is on this side. The H1 value is given as 10 watt per meter square degree centigrade, which can also be written as Kelvin. And then the temperature on this side is given as 20 degrees centigrade. T infinity 1 is given as 20 degrees centigrade. On the other side, you have H2, which is equal to 40 watt per meter square Kelvin, and T infinity 2 is given as minus 10 degrees centigrade. So you're done with this. This one is taken. Yeah. See here, this is not the K. The K value of this is given as 0.78. The thermal conductivity of glass is given as 0.78, and for space it is given as 0.026 watt per meter Kelvin. This is what is given, and then what else is given to you? This thickness is taken, and these are separated by 10 mm. These are separated by 10 mm. So this particular distance, I can take it as 10 mm. So this is what I have. So now that I have written everything that is given in question, I have written everything that is given in question. 10 mm is written, 4 mm is written, H1, H2, everything is taken. Now, let me draw the resistance circuit. Okay, if I draw the resistance circuit here, the resistance circuit goes like this. Okay. There are 5 resistances here. Okay, let me put all those 5 resistances here. Look at, see, first resistance is the resistance due to the convection. Okay, on the atmosphere side, you have resistance due to convection on side 1. Okay, on the other side also you have convection side too. So this is one atmosphere, this is the other atmosphere. Two atmospheres you have taken R convection or R convection too. And this being R conduction one. And the other side also you have 4 mm thick. So what you can write is this is also R conduction 1. Both values will be the same. You need not write it 2 times. So that's why I'm writing with the same name. Okay, the other side also. But whereas here you have air. When you have air, generally you take something called as convection resistance. But here, the convection resistance value he has not given to you. What he has given is, he has given you this 0.026 watt per meter Kelvin. Watt per meter Kelvin is thermal conductivity. So what you have to do is, you have to take conduction resistance itself here. You cannot take convection resistance because you don't have the H value for the air here. Although you can take it, but it is appropriate to take the conduction resistance itself because the air is not moving, it is a stagnant. So stagnant fluids will contribute to conduction, not to the convection. So it is appropriate to take the conduction resistance itself. And on one side of your uh, resistance circuit, what you take is T infinity 1, and the other side you take T infinity 2. So this T infinity 1 is 20 degrees centigrade, T infinity 2 is minus 10 degrees centigrade. And you will have so many temperatures here. You can name them as per your convenience: T1, T2, T3, and T4. And the heat transfer direction is this one. This is Q. Got it? Now, what he's asking you to find, he's asking you to find, determine the steady rate of heat transfer through this double pane window. So you have to find out what is Q. So to find out that Q, what you should take, this Q is equal to the temperature difference. The temperature difference, you know, for these two. So what you should take is T infinity 1 minus T infinity 2. You take it in the numerator, and the denominator you will have R total. R total. What is R total? The sum of all these resistances, where R total is equal to R convection 1 plus 2 times R conduction 1 plus R conduction 2 plus R convection 2. So what you have to do is, you have to find out all these values here. R convection 1. Convection formula for resistance is 1 by HA, and this is equal to 1 by H on the side 1 is given as 10 watt per meter square Kelvin, and the area is 0.8 into 1.5. This value is given on the top of the question. You can see 0.8 meter high into 1.5 meter wide. That will contribute to the area. So that's what is your R convection 1. Then R conduction 1. R conduction 1 is equal to L1 by Ka. L, what is L here? It is the thickness of that glass, thickness of this glass. What it is, this thickness is 4 mm. So you can take that 4 mm here and substitute it in meter. 4 into 10 to the power of minus 3 will be meters. And K value, the K value for the glass should be taken, and it is around 0.78 watt per meter Kelvin into area. Anyways, remains the same, 0.8 into 1.5. So this will give you a value. And then R conduction 2 is for the L2 by Ka. It is 10 mm here. 10 mm is the gap between the two glasses. So 10 mm in meters into 10 to the power of minus 3 have to convert. And the air thermal conductivity, this is a glass thermal conductivity. This is air thermal conductivity. It is 0.026, isn't it? It is 0.026 into 0.8 into 1.5. So That is R conduction 2. And what is required? R convection 2 is required. It is 1 by H2A. This is H1A, this is H2A. 1 by H2 is, what is the H2 value? It is 40. 40 is given in question. 0.8 to 1.5. So you'll get all these values. Somebody tell me these values. R convection 1,
0.08.
0.0833.
Same.
0.833 Kelvin per watt. Conduction
4.273 into 10 power minus 3.
4.273 into 10 to the power of minus
3.
3 Kelvin per watt. Good. This one, no? Next, R conduction
0.3205. 3205.
0.3205 Kelvin per watt. Good. R convection to
0.020.
2083 Kelvin per watt. So you simply substitute all these values into your Q. You will get the value for Q. So Q is equal to T infinity 1 is 20 minus 10 by the sum of all these three. 0.0833 plus 4.273 into 10 to the power of minus 3 plus 0.3205 plus 0.0208. This is what you have in denominator. So tell me what is the value of Q?
69.46.
69.46 watts. Very good. Right. Did you ask anything else? Question? And the temperature of its inner surface for a day. Okay, he is asking you the temperature of its inner surface. Means this one he is asking. That is T1 he is asking. If you want T1, what you have to do? You have to take this thing. Okay, if I take this part here, what you get? Okay, let's put that one here. So from this, what I can write is, if you want Q from this one, Q is equal to the temperature difference, T infinity 1 minus T1 by the resistance R convection 1. You know the Q value now, it is 69.46. And the T infinity 1, you know it is 20. T1, you don't know, you have to calculate that. R convection 1 is 0.08.
14.2.
0.083. This will give you T1 as 14 point, what, 2 or 3?
17.
2.7 is almost 2. So 14.2 degrees centigrade. Good. See, what is the Q value for your single pane window? Is P actually single pane window and double double pane. See, for single pane window and double pane window, you have the same environment on the either side. Okay, on the room side and the atmosphere side, you have the same environment taken in the rooms that you have done. So Q value, what is the Q value in the single pane window? It is around 260 something like that. Somebody tell me, what is this one here? This is 69 watts here. In the previous problem we have done, what is this Q value for single pane window?
266.335.
266.3.
3. Yeah.
Yeah, 3, 4 you can take. Okay. What is the T1 value?
minus 2.20.
minus 2.20. Here it is 14.2 degrees centigrade. See, if you have a double pane window, look at the reduction in the heat transfer. There is a huge reduction in heat transfer. Okay, that's what the advantage of your double pane window. See, that's what the advantage of your air. Okay, air is having very less thermal conductivity. If you trap the air in between these two glasses, see how much it has reduced. It has reduced almost by 200 watts. Reduction of heat transfer by 200 watts is a huge reduction. And why did it happen? It is because you have made use of the thermal conductivity of air. Okay, air having a thermal conductivity of 0.026 watt per meter Kelvin. So that thermal conductivity is made use of, and that is the reason why you could reduce the heat transfer hugely. Also, you could maintain very good temperature on the window side of your room. The room side, if somebody touches the window, they'll feel comfortable. But here, it's not comfortable. Not comfortable to touch, whereas it is comfortable. So I hope you got the point in this particular problem. Okay, this is not just a problem. See, every problem I explain, there will be a concept behind that particular concept. You should think for yourself and understand. Okay, see here this problem reduction is huge if you go for a double pane window, making use of the thermal conductivity of air. Okay, maybe you can make a note of this particular point. Okay, right. So we will move on to the next problem. We will take one more practical problem today. The problem will be for uh, see this particular problem is a problem that will be representing your wall. Okay, the normal wall that you have in your home or anywhere. Whenever you see wall, this is how the wall will be like. Okay, the wall will have a brick, and then around brick you will have plaster. That is a kind of a combination of your it is a mixture of what you call the cement, sand, the other things. They are mixed with water, and then they are poured here, and then it, over that you will coat with the layer of foam, something like your what you call what I can say is a kind of paint or a layer of smoothness and all that. So this particular problem, what it is representing is it is representing the real-time wall. Okay, what is the heat transfer that is happening through this wall? We are trying to find out in this particular problem. Okay, what he has given is he has given you a 3 meter high and 5 meter wide wall. So if I have to take the area here, the area is 3 meter into 5 meter. This is the overall area. I mind you, this is overall area, right? And then it is consisting of 116 centimeter long and 12 centimeter, sorry, 22 centimeter cross section horizontal bricks. So this is 22 centimeters and this is 16 centimeters he is giving. This is 22 and this is 16. And that's what the dimensions of the brick he has given. And the thermal conductivity of this brick he has given, it is 0.72 watt per meter Kelvin is given. And then he's saying that there is also 2 centimeter thick plaster layer. This is 2 centimeter thick plaster layer on each side of the brick. This side 2 centimeters, this side 2 centimeters. On your left and right, there is 2 centimeter thick plaster layer and a 3 centimeter thick rigid foam on your left. You can find that there is a pink color foam. Okay, this is not pink color in reality, but it is shown here in this particular diagram. It is 3 centimeters that is also given, and it is having a thermal conductivity of what 0.026 watt per meter Kelvin. This is also given. And the inner side of the wall was shown in the figure. That is, this is your inner side. Okay, inner side of room. Then indoor and outdoor temperatures. T infinity 1 is 20 degrees centigrade. T infinity 2, it is minus 10 degrees centigrade. The convection heat resistance here, the H1 on this side is, here it is given, it is 10 watt per meter square Kelvin. And here it is given as 25 watt per meter square Kelvin. So that is what is given respectively, assuming one-dimensional heat transfer disregarding radiation. Determine the rate of heat transfer through the wall. What is Q value? He is asking you to find. So what you have to do here, you have to draw the resistance circuit. Okay, for this one, you can draw the resistance circuit. Your plaster again. So it's actually a simple problem. Okay, you have so many resistances due to so many areas that are persisting there. But you look at this R plaster is not the same as this R plaster because the dimensions of this R plaster are different compared to this one. So let's call this R plaster 1 and R plaster 1. And because these two dimensions are same, I'm taking it like that. And you will have one more resistance, that is the resistance due to the convection on the other side. Okay, so these are all the resistance that are prevailing in your cases are convection too. If you can find out these resistances, you can get the Q value. The Q value is depending on your T infinity 1 on this side and T infinity 2 on this side. Q is actually flowing like this. So Q is equal to T infinity 1 minus T infinity 2 by R total. And then if you take R total, this is the sum of all these resistances. Yes, ma'am, please ask.
There is half of 2 weeks, no sir. Why shouldn't we take the resistance for those 2 weeks?
Yes, that's a very good question. See, here, what is the area given? It is 3 meter by 5 meter area. So if I sum this 1.5 plus 1.5 plus 22, what is this value? It is 22 plus 3, 25 centimeters. But in reality, what is the height of it? It is 3 meters height. Okay. But I'm not taking only 3 meters height here. What I'm doing is I am considering a repeating unit here. This is my repeating unit. What I have shown you in red color here, this is my repeating unit. This is very important thing when it comes to this kind of problems. In reality, you cannot keep taking each and everything. So you will take one repeating unit, and for this repeating unit you will calculate, and the remaining part into so many units you will do that. So that's why I'm taking a repeating unit here. You got my point, ma? Is it clear? It is 25 centimeters here, but actually it is 3 meters. But I'm taking 25 centimeters only because I have to, take the repeating unit concept here. Unless I take the repeating unit concept here, I cannot solve it. That's a very good question. Now, let us move to this R convection 1. What is it? 1 by H1A is equal to 1 by H1 is given as what? It is 10 watt. Let me write the 10 watt here. What is the area here? Area perpendicular to the direction of heat transfer. So What is the wideness of it? The wideness of it is 5 meters. It is given as 5-meter wide wall, but the height is only 25 centimeters. As I have shown you here, it is just 25 centimeters. So what I should substitute here is 5-meter wide. Should I write this M here? Let's get this. 5 into 25 into 10 to the power of minus 2. This will be your area. Good. So calculate that next. R foam. This is a conduction resistance. So I should take L by Ka, and it is 1 by K value of foam is given in question as 0.026. 0.026. If you observe this value is similar to that of your A. Right. Area is 5 into 25 into 10 to the power of minus 2. Similar area you will have here. The area is same in both the cases. And then R plaster 1. And R plaster 1 is equal to L by Ka again. See, L is not 1 here. I guess it is 3. Okay, I should change this to 3 centimeters. So 3 into 10 to the power of minus 2. And R of plaster here is given as 2 centimeters in the question. So I should write 2 into 10 to the power of minus 2 by the K of the plaster. K of the plaster is given as 0. K of the plaster is not given in question. Thick plaster inside the rigid form is given K value. Horizontal bits. Let me check this.
0.22.
It is given in question.
Third
Yeah,
line.
it is given in question. Yeah, very good. It is 0.22. So the K value of the plaster is 0.22 into the area. Area remains the same in this case, 5 into 10 to the power of minus 2. We'll get this. Yeah. Then after R plaster 1, you have to go for R plaster 2. R plaster 2 is again L by Ka. The L here in this case is 16 centimeters. This 16 centimeters you can see here. This is given here. So this is whole thing till from here to here. It is 16 centimeters. So I can substitute that 16 centimeters here, 16 into 10 to the power of minus 2 by the K value of the plaster. Anyways, it is 0.22. And here you have 5 meters wide. And what is this area here? This 5 into this 1.5. On both sides, it is 1.5. So what I should multiply here is 1.5 into 10 to the power of minus 2. This will be area perpendicular to the direction of heat transfer in case of your R plaster 2. And then R brick. See, only areas are important here. Areas, the dimensions, all the geometry things should be taken care very well. Okay. L again is 16 centimeters in this case, similar to the previous one. K of brick is given as 0.7, what is 0.72, 0.72. The wideness is anyways 5. And what is its height? Here the height is 22 centimeters. So it is 22 into 10 to the power of minus 2. So I hope you are done with everything. Yeah, R convection 2 also should be found out. R convection 2 is equal to 1 by HA is equal to 1 by H value on the other side is given as 25, and the area is 5 into 25 into 10 to the power of minus 2. So somebody tell me all these values of R convection 1 and R foam and all. What is R convection one form value? Did anybody calculate?
0.08.
0.08. 0 point.
Sir,
Hello. Hello.
0.08.
0.08. Yeah. 0.08 Kelvin per watt. This one. Next, R foam.
0.923.
0.9.
0.923.
923 Kelvin per watt. Okay. This one.
0.0727.
0.07.
7 Kelvin per watt. This one. R cluster 2.
9.6.
9.63 into something. 10 to the power of. Huh?
696.
Your voice is not audible. R brick and R
696.
convection. Your voice is not audible. It's not clear. Somebody tell me what is R cluster 2, R brick, and R convection 2.
9.69, sir.
9.69 Kelvin per watt. And this one.
0.202.
0.202 Kelvin per watt. Good. R convection to
0.0.
0.0. Your voice is not audible. You start speaking. Your voice is not audible.
0.032.
0.032 Kelvin per watt. Okay, good. Right. What you need here is something called as R equivalent. You should need R equivalent for resistances that are in parallel. So for those resistances, you have to calculate this R cluster 2 times and R brick. So 1 by R brick plus 1 by R cluster 2. Since this is 2 times, I can put 2 here. Okay, 2 times. So this value R equivalent.
4.99.
R equivalent, you have calculated 4.99. You can substitute all the values and you will get this. Right? So this is how you will get the R equivalent. So what you have to do next is Q is equal to T1 is 20 minus 10 by the R total. Sum of all the resistances you have to take here. Sum of all resistances will be like R convection. In first place, you will have 0.08 plus after R convection, what you have? R foam, it is 0.923. 0.923 plus after foam, you have plaster 0.0, 0.07, 0727, 727. Since this is 2 times, I can multiply it with 2 here. Other side of the brick also it is there. So that's why I can take it like this. And here I'll get R equivalent, it is 4.99 plus the R convection to it is 0.032. 0.032. So that's how we will get Q. Tell me what is the value of this Q.
$4.86.
Yes, please tell me. 4.86. 86 watt. Okay, this is what you got. But this particular q what you have calculated is not for the whole area. So in order to calculate it for the whole area, what you have to do is you have to take this q, you have to take this q in terms of the area. That is, if you have to convert this into that, q by a will be q. This is nothing but the heat flux. That is 4.86 by the area. What is the area? 5 into the value that is given in question is 5 into 3. So 5 into, tell me, what is this?
0.324.
Sorry, this should not be 3 here. First, I should put it for here 0.25. That is 25 into 10 to the power of minus 2. 25 into 10 to the power of minus 2. Tell me this value.
3.88.
3.88. See, this is the value for this particular area. This particular area that you have to take. Now, if you want it for the whole area, what you should do is 3.88 into the whole area you have to multiply, because this is measured in watt per meter square. Write it here. The time is going fast, so 5 into 8 now. Is it 5 into 8? Given in question? Yeah, sorry, 3 into 5 it is given in question. We have to write. So this will give you the overall heat transfer. Somebody calculate and tell me this value. What is this?
58.32.
58.32 watts. Right? So this will be the heat transfer that is happening throughout the wall. This is how you can consider. Okay.